everybody. So we left off yesterday with this spin and charge result detection, understanding how that actually works, and now I actually want to apply this now to a few problems that were introduced by many of the lecturers actually previously, and see if we can see those phenomena actually also in the experiment. So the first thing we can do, for example, on a 1D chain of Fermi-Hubbard chain, we can up and down particles. We can just look at a very standard thing, which is just a 2-point correlator, SE inside I, correlated with SE inside I plus D. And then you can actually see this nice anti-ferromagnetic correlations. Remember, as Thierry told you, even at T equals 0 in 1D, we would not get any long-range order. There's always this algebraic decay that you have on top of that. Here we're still kind of dominated for larger distances by thermal fluctuations. That's why you see this is kind of exponentially damping. You don't see the algebraic decay where we basically key in on these two first sides, but it's too hard to see basically. So you're basically here already in the regime where you're limited by the thermal fluctuation. But keep in mind, even at T equals 0, you would have the strong envelope given by the algebraic decay of the system. Actually, here's a single snapshot. Remember, we take this is a measurement that comes out of taking many of these snapshots, averaging them, and calculating SVSE correlations. Okay, this is one where actually is this nice near antiferromagnet. So remember, these were the two lines we imaged. We can reconstruct the original line by that. So this was down, up, down, up, down, up, down, up, down, up. Of course, remember also that in the Heisenberg antiferromagnet, this is a very rare configuration. Actually, this state has very low amplitude in the true Heisenberg antiferromagnet. This is actually the ground state of the NEL, just the SESE spin 12. So, but of course, from time to time you see it, and actually in the subsequent parts of the talk, as before, are just to symbolize an antiferromagnetic state, a Heisenberg antiferromagnetic state. We'll still think of it in this picture.
Yes, can I ask a question? Do you have an independent measurement of the temperature of the system, or is it difficult?
Well, this we can just by comparing to theory, basically. So in this case, this was about, but this is actually also your post-selected to total magnetization 0 because finite magnetization fluctuations also reduce the correlation length in this case. I think here this was probably 0.5, this is post-selected 0.5 or 0.4 to exchange. But not independently, right? Just to come in this case, in the unknown.
The reason I'm asking this is because normally the coefficient in the exponential decay depends on the power wave. Yes. So that means a way to re-extract the power wave together.
Okay, so let's go now to this fundamental topic that Thierry introduced you to about disfractionalization. So let's do a dynamic experiment where we really ask, can we decompose an elementary particle like the electron into its quantum number. So in free space, we take an electron with charge -3, spin 1/2, and we ask, can we make out of that two particles, one which carries just the charge quantum number, and another particle which carries just the spin. And we know, of course, in free space, this is impossible to have to get with an elementary particle. But we also know now from Thierry's lecture, if you just replace particle by quasi-particle, and you do that in a solid state system, then you can actually fractionalize an elementary particle into two quasi-particle instantaneous, one which carries the charge quantum number and one which carries the spin quantum number, for example. And this occurs in the fraction Hall effect, or in other cases you have this fractionalization processes, but the most common one, maybe simplest case, is the one that Thierry introduced to you, is precisely these 1D antiferromagnetic chains, where you get the speed-on and the hold-on excitation in the system. We also speak of deconfinement in this case, in this 1D case, where basically these elementary quasi-particle excitations can be separated over arbitrary distances. So they are not bound to each other in any way. They're completely deconfined as we see. Okay, so how we do the experiment is precisely what Thierry told you in this Dynamical experiment. We take this Heisenberg antiferromagnetic chain, and we just remove a particle here, basically, dynamically. We shine a laser on that side and just blow it up. Okay, that's the same as injecting a particle, an electron with spin 1/2. Here we just basically think of injecting an anti-electron with spin opposed to the one here to remove some particle here. And so now you have the hole there, and you see actually as a function of time what happens. In this cartoon picture, you have this charge, holon, propagating, for example, here to the right, and the spinon excitation left, which carries the spin 1/2 fractional quantum numbers propagating in the other direction. And because these two quasi-particle excitations have very different dispersion relations, their propagation velocities are, of course, also dramatically different. Basically, the spinon is something proportional to J exchange, whereas this holon propagates basically at the speed of a kind of tunneling of single particle tunneling. Okay, so there have been, of course, previous experiments on this, a little bit more complicated to interpret. Mostly spectroscopic experiments, maybe the most famous one by Amir Yacobi's group in 2005. But all of this was these spectroscopic measurements. I think the first people who, in the context of cold atoms, brought up the idea that you could see this actually in real space and time were Copenhagen Pollard, Uli Scholberg, and Felix Berger in this beautiful paper, where they precisely showed that if you would make somehow a bump here of charge spin, then you would see that fractionalized in these two contributions that you can see here. Okay, yes.
But that's actually, that doesn't prove spin charge separation.
I will show you, yes, I will show you meta quantities. I agree, it just shows two different velocity branches. And I think with the correlators that I will show you, we can prove correlate fractionalization. But bear with me for a moment. So, first thing we can do, we can measure, for example, in this chain, we remove a particle. Here's the lattice, here's time, we remove a particle, and then just plot the average hole density, okay? And you actually see having a hole, again, it's like a particle, it just does its quantum walk on the lattice that we encountered before. And you really see this nice coherent quantum walk with the interference structure as we had calculated before in the lattice. Okay, this is the probability distribution of the hole. We can do the same thing now for the spin, and for that, for the spin, we look at a different quantity. We look at the C1 correlator, which is the next neighbor spin correlations. Okay, so we ask how are the next neighbor spin correlations modified. They should be antiferromagnetic within the undoped chain, but when we remove that, we see these C1 correlations also spread out. Here, because of temperature, it's a little bit also, the coherence is taken away, but the cone kind of velocity still matches pretty well with the maximum velocity in this case. So now we can extract the velocities, and I would say, usually you would say that's not enough proof, but we can do that as a first step. We can look at the velocity of the spin, this excitation, the C1 excitation, and we can look at the velocity of the whole excitation, and we see actually that this are very different. So the whole spreads very fast on the time scale of single particle tunneling, and the spinon here on this time scale of exchange. And so with Fabian and what we looked at comparing this to theory, and this agrees actually very well with theory. Okay. But you can ask, yes.
If you do it at the level of one particle, it is a proof. If you do it at the level of a collection, a large number of particles, then it's not.
Yes.
So from this point of view, what you guys, since you do it with one particle, that is already a proof.
Okay, but let me show you a correlation function which I think is more meaningful to show really fractionalization, and which is kind of this non-local correlator that I plot now here. So this is the correlation where I look how are the spins ordered around the hole. So this is a non-local correlator where I correlate the spin on this side and on two sides away, conditioned on having a hole in between. Okay. Now, if you start out and you remove the particle from this picture, you'll actually see if you just remove it abruptly, actually this correlator initially is positive. Okay. So kind of the spin is still attached to the hole, the spinon is still attached to the hole. But as the time propagates, as the spinon separates in the other direction, you actually see that this spin-hole spin correlator will turn negative. Okay, will turn negative to the background value. Now you can see you have this free hole which has no spinon attached to it. It got rid of the spinon and spinon sits somewhere else. We have to find other ways to detect it, but we have to really see it at another place, basically. And this is indeed what we actually see also in the experiment. You start out with this positive spin-hole spin correlator, and then rather rapidly this hole sheds itself from the spinon and becomes negative. Actually, what's interesting in our case, because we have the trap, remember the hole spreads out, but then the hole comes back. Spreads out, comes back, spreads out, comes back. And actually when it comes back, there's a small recomposition of your original electron. You know, there's a revival when the hole connects again to the spin, to the spinon, and that's why you see this small peak actually occurring when the hole kind of comes back to the original point. So this is initially the linear spreading, and then it comes back to the original site, close to that. But of course the spinon is propagated out also a bit, so it's not, cannot revive completely, but you see a partial revival, then it goes away again and kind of partial decomposing the original elementary particle that they put into the system. But I think this is, for example, a correlator which shows you the fractionalization. And what's interesting, I think, what you see, what you need to show, what you need to have to actually show this from an experimental point of view is you need these non-local correlation functions. You need something beyond the two-point correlator to actually show that. Okay. Let me actually also ask now, look at how do we, can we now, the next question is how can we see the spinon? Can we also see the spinon? And for that we did the following. So we're actually looking at the magnitude of magnetization in a certain area in some windowing function. So I'm just measuring the SE operator summed over some sides with some windowing function, which for example we could take to be a Gaussian function. And since we don't know if we're kicking out a spin up or a spin down particle when we make a hole, we have to look at the absolute value of this magnetization. And now again, this is a non-local operator because to calculate the absolute value of this magnetization in a certain windowing area, you need to first make the measurement, sum up all the Z values, and then put the absolute value of that and average. So you really need to see everything on this chain. And actually when we do that, this is actually also related to the fluctuations of the magnetization in a certain area. You can do the case where you have not removed the particle. This is kind of your background, the red signal. And then you can do it with the blasting, where you remove the particle and now you see the blue signal. You can take the difference of the two, and this is kind of now your excess magnetization, how it's spreading out in space. Okay, how the spinon wave packet is actually spreading out in space, how it's initially localized here around the whole area, and then how it's spreading out. And actually here you can see even a little bit reminiscent some different structures of a coherent walk of the particle of the spinon propagating through space. Okay. So we can both, I think both those correlators are non-local correlators, and they are kind of interesting because I think they more or less, as directly as you can from the experiment, show this fractionalization of your elementary particle with these two constituents here, and we can directly see that also. All right. Now, actually, what I want to do next is connect this dynamical experiment that we saw to the ground state physics that Thierry talked about before, because this spin-charge separation we see in 1D in the dynamical features is actually intimately connected to ground state physics. And now what I want to do is I want to ask first the question, now a little bit to your intuition again, how the ground state looks like for this case when we have a hole in these antiferromagnetic spin chains, many holes in these antiferromagnetic spin chains. If we have a single hole, you basically can think of the hole, if it wants to minimize its energy as any particle, it wants to delocalize. Right? It wants to spread out as much as it can to minimize kinetic energy. The spins, on the other hand, want to align antiferromagnetically. So you have the competition of those two effects, antiferromagnetic order and hole delocalization. And now you ask, what is the ground state of the system? And what you actually find is the following. The best way you can arrange your particles is to have the hole being in a superposition of everywhere in the system. So the hole is delocalized. And at the same time, you actually have antiferromagnetic correlations around this hole. Not ferromagnetic, but antiferromagnetic correlations around this hole. This gives you a lower energy, and this is the ground state of the system compared to this first excited state that you have. So a first message that you should take that has been also emphasized in Thierry's and Fabian's talks is a hole in a 1D chain is like a quantum domain wall for the spin, the antiferromagnetic background. So it's really not just a local effect, it has a global effect on the system because the parity of your antiferromagnet, which is just the order, let's say down, up, has parity +1, and up, down would have parity -1. This hole changes the parity on the other side of the hole. So it really not just has a local effect, it has a global effect, and therefore Thierry was speaking of this topological excitation that you can have in the system. So we can try to measure that. We can first look how are the spins aligned around the hole, and here's the first example of this non-local correlation function that we need to do to measure that. So we are measuring the spin on this side, correlated with the spin two sides away, conditioned on having a hole in between. Okay, that's, again, this 3-point correlator is something you cannot measure in a condensed matter experiment. So that's why it's so wonderful to have these quantum gas microscopes to look at these effects. And for the undoped chain, you see we have this standard antiferromagnetic order, and then just let's go to distance 2, you have a single hole, indeed your antiferromagnetic correlations are precisely reversed. You go from ferromagnetic to antiferromagnetic correlations. But we can do better than that, because this just shows the local effect, kind of ordering the hole. We can look at the entire antiferromagnetic ordering beyond or within kind of the distance of the hole. So now I'm plotting again the correlator here, this 3-point correlator, spin at site I, correlated with spin at site I plus D, conditioned on having a hole at site I plus S. Now S can now have two values which are important. S can be smaller than D, then the basically hole sits within the distance of the spins you're correlating, so you're in this situation, if S is smaller than D, or you're in this situation where S is larger than D. Okay? And that should have profoundly different effects, because remember, when S is smaller than D, you have this parity flip of the antiferromagnetic background. And this is what we see. So here you see again the spin-spin correlator, conditional having the hole at this site S. So you see nice antiferromagnetic ordering, down, up, down, up, down, up, down, up. And now when the hole is in between, you see again you have nice antiferromagnetic ordering, but everything that was blue has turned to red. And so it's really the entire antiferromagnet beyond that hole has shifted as a complete block. Okay, so really we see this strong non-locality of this effect of the hole acting on the complete entire system in this one configuration. Okay. Actually, what's also interesting is that you can put as many holes as you want between these 2 points of the spins. They will stay antiferromagnetically ordered. Yeah? So the holes basically are as they would not be present and just produce effectively the coupling. So now we know what one hole does, but then you know also what many holes do. And many holes, basically each time there's a hole, we set the situation simple. Each time we find a hole, we get this parity flip. Okay, so every time there's a hole, the parity of the antiferromagnet flips by -1. And now what Fabian was writing down yesterday, I just put in this cartoon again. If you stare at this image, actually if you would somehow remove the holes and go to this fictitious squeeze space, this actually looks like a perfect Heisenberg antiferromagnetic. Okay, so getting rid of the holes, going to the squeeze space, you see that there is a kind of very simple order in this state. You just have to get rid of the holes, squeeze them together, and then you see this nice Heisenberg antiferromagnetic. And this actually, this statement you can make exact. You can actually write the many-body wave function of this strongly interacting system for very large U over J in an exact form that was derived in beta-Untitled solutions by these two wonderful papers in the following form. This many-body ground state is a product of spinless fermions defining the position of where the electrons are, and then a magnetic part, which is the Heisenberg antiferromagnet, living on the positions of the electrons with a perfect antiferromagnetic order on this fictitious lattice. And you can see this product, this factorization in the density part and the spin part. This is in the ground state the manifestation of spin charge separation that you have. Okay. That we saw in the dynamical effect, but that we also see here as a kind of a very strong feature in the ground state. You also saw yesterday that you can reveal this order in another way. You can either go to squeeze space to see that there is a nice antiferromagnet, but you can also look at these string correlators, which basically take care of the fact that whenever there's a hole, you basically flip the sign of the spins you're correlating by -1. So this operator just does the following. Whenever it crosses a hole, it flips the sign of the expected correlation by -1. And you see that's important, because if you don't know how many holes you have in between here and here, if the number of holes fluctuates, then the correlation between this side and this side will be 0. Because if there are a random number of holes in between, each time there's a hole that flips by -1, if you average the result, then you would expect no correlation between those two sides. I'll show you that. So to see the holes is absolutely crucial to flip this kind of expectation value to the right. Okay. And maybe this, just to put this in context, brings me to this, way of how we define the order in condensed matter systems. And the typical Landau paradigm that you probably all have heard of is the idea that the system shows this order if you have to an observable A, for example, that you measure two space points x and y, and if its correlator is a constant as x and y go to infinity, the distance between them, then we'd say the expectation value of A is our order parameter in the system. And some examples of these local order parameters are magnets, antiferromagnet, we see condensate wave function, we see a superconductor. Those are all examples of local order parameters. Why do we say local? Well, because if you know the order at some point here, for example, in a ferromagnet, then you know the order everywhere else. Okay, if you know what's going on at one point, local point, you know how this order manifests itself at any other point in space. So this local order is sufficient to describe that. But by now you've also heard that it's not a general classification scheme of matter. Indeed, we have these beautiful examples of these string correlators, for example, where you need to not only know what's going on at point x and y, but you need to know also what's going on at an observable B on all space points between x and y to reveal the correlations in the system. So this is an example of these more non-local correlation functions, and also there are examples in higher dimensions where this occurs. So basically, you just need to know that these are difficult to reveal, of course, in the experiment, because you need to know not only what's going on at these 2 points, but you need to know what's going on at every point in the system. Okay, that's why people speak of hidden order parameters, because nobody thought that you could measure these. They're like more theoretical concepts, but you can't really measure that. And you really need this global view of the wave function, okay, of what's going on in the system. And that's really difficult with the quantum gas microscopes. At least to some extent, we can measure these for some observables. Okay, so now, yeah, actually the Haldane insulator, actually Thierry already mentioned yesterday for a spin-1 chain, which you could actually realize in an effective way with long-range interactions with bosons. But for a spin-1 chain, you have precisely the same situation, where the spin-1 Haldane chain would show this type of order. Now we have a spin-1 chain. Let's imagine we have 3 SZ components, 0, -1, and +1. And in the Haldane chain, the order would look precisely like this hidden antiferromagnet we've seen in the spin-1 half chain. So you have this random zeros between these plus and minus ones. So again, if you squeeze out the zeros, you see -1 is pursued by +1, by -1, by +1, by -1. But in order to reveal these correlations, you have to know how many zeros there are in between to predict what the next one here is going to be. So this is just in hidden antiferromagnet like the case we've seen before, with one difference. Here it's true order parameter, the string correlator. It does not decay algebraically. If I would calculate the string order parameter for the Haldane chain, it would give a constant value. Okay. In our case, it decays algebraically. So if I let me go back here. If I look at this case here, this correlator, this string correlator for the spin-1 half chain still shows algebraic decay, because effectively the magnetic part has this algebraic decay, whereas in the spin-1 chain the big difference is that this string correlator actually really goes to a constant value for large distances x and y, so that's why in that case you could say we have true topological order in the system compared to the spin-1 half chain, but the detection actually is precisely the same. So let me show you this now. Enough theory. Let's look at this in the experiment. So here we looked at chains, 1D chains, which we doped with random fillings from 80% doping to 10% doping. And you actually see, if you just look at the 2-point correlator, if the spins sit right next to each other, of course they have to be antiferromagnetically aligned. There can be no hole in between. So distance 1 is always antiferromagnetic. But beyond distance 1, everything is flat. So if you see this data as an experimentalist, you would say, well, there's just no antiferromagnetic order in the system. Okay? But now we can do better because we know where the holes are in each shot, and we can measure the string correlator, and now we see that we can recover the antiferromagnetic correlations that are in the system. Okay? So we can truly measure this hidden order parameter, and that's very nice that we can reveal this hidden order in the system. I guess the message, important message to convey is that, these non-local operators, which were truly believed to be not accessible to experiments, are now accessible to experiments. They typically find manifestation also in some dynamical properties of the system, like the spin charge fractionalization we saw in this case. But they are, in most cases, actually connected to some non-local order in the ground state. And this can be very complicated, this non-local order in the ground state, but the point is, it can be measured. And I think that's very interesting. Okay, I want to go a little bit also into what Thierry also told you in incommensurate antiferromagnetism. So I want to talk about these holes. When you put them in, Thierry showed that actually they organize in a subtle way. they actually give you this cosine modulation at basically density 1. We get this nice antiferromagnetic ordering, but the holes kind of squeeze in a way that they just stretch out the antiferromagnetic wave. In the same way, if we magnetize the system, these excess spins, they also kind of squeeze in the antiferromagnetic in a subtle way such that the antiferromagnetic wave vector gets stretched out in space. And this is, of course, one of the celebrated predictions of multi-molecular theory. Now, experimentally, it was tricky a bit to measure that because you see you need to precisely fix the density or the magnetization to see that. If that quantity fluctuates, it will just average out basically. You will not be able to see those kind of oscillations in the system. And now, of course, you could ask, do we have this control? And a priori, if you look at histogram of our experiments, we do not have this control. So this is just, histogram of distribution functions, how many atoms we have, what the magnetization is in the chain, how many doublons, how many holes, just counting, doing statistics over the single images. And you see, well, that the magnetization fluctuates pretty widely. The density also can fluctuate here. But now we can do a trick, which is of course nice. We can now precisely post-select the data on a certain density or a certain magnetization. Okay, so I can just take only those images from subsets of images where the magnetization was 0, or where the magnetization falls within a certain range. Okay, and look at the data in that range to fix the magnetization and the density of my particles in the system to have perfect control over it. And if we do that, we can indeed see this nice stretching of the antiferromagnetic wave vector. So here we did basically hole doping, so we introduced holes or doublons into the system, and you can actually see very nicely how the two-point correlator, this antiferromagnetic wave vector, indeed linearly kind of stretches out as you dope the system with holes or excess particles in the system. Same for excess spin. So if we look at the excess magnetization into the system, then you can indeed see also how it stretches out linearly as a function of magnetization. As you see here, this spin density wave vector going away from pi here as we mentioned magnetization away from 0 to kind of negative or positive values here, how this stretches out linearly for this excess speed. And this actually is nice because Thierry showed you that we learned that holes are like quantum domain walls in real space. Spinons actually are like quantum domain walls in squeezed space. So it is spinons that we encounter also lead to a parity flip of the antiferromagnetic order in this squeezed space, and this is precisely what we see here. So this is the squeezed space picture when we have no spinon. When we have a spinon, measure the correlations across that, we see how the antiferromagnetic correlations are again flipped. So we can see all these kind of effects of the holes and the spins directly in the system. Actually, here's a single snapshot where you can see the spinon, although in single snapshots, again, it can be completely random, but here's, for example, a case where you see those two up particles spins sitting right next to each other. Okay? But of course, single snapshots in a Heisenberg antiferromagnetic measure density basis, it could be just a random occurrence that happens, that the spins show up to be up next to each other, only really, statistically averaging over many of those images. Can we say something about the presence of these spinons in the system? Okay, I want to now go on with the case of 2D, just to show you very quickly, and Fabian, because Fabian will talk much more about this in his talk, about how this actually changes in the 2 dimensions, how the situation dramatically changes in 2D. So again, now we're back to the 2D case. We want to know what the holes are doing, and we want to do this Gedanken experiment of just putting a single hole in this antiferromagnet. Okay, so you would say, wow, that cannot be such a difficult problem. Well, it turns out that 3 of the most celebrated theoretical physicists worked on that. So this is actually a dream team of theoretical physicists. I'm looking precisely at that, Charlie Kane, Patrick Lee, and Nick Reed. I'm looking at the motion of a single hole in this quantum antiferromagnet. Okay, so that already shows you if you have to take 3 of the best theoretical physicists, it's not such a trivial problem actually to try to solve it. Okay, let's again think of it in an intuitive way, building on what Thierry told you already yesterday in Fabian, that again we have this competition between magnetic and kinetic energy doublons, but as Fabian said, this is like the same thing because of this particle hole symmetry that we have in the Hubbard model, so we work now with excess charge carriers. And now we see that if this, for example, spin up moves here, the doublon has moved. But in the contrast to the 1D case, now it leaves behind this array of fluid strings behind it, fluid spins behind it. And if it moves further, this cost even increases. So the more it moves, the more fluid spins it leaves behind. And that already shows you that this excess doublon cannot separate, cannot move freely through the lattice, cannot separate from this spinor part that we saw here, that we saw in the 1D case. So there's a dramatic difference between both, but we can still ask what is the best configuration of the particle to minimize the overall energy in the situation. And naively, you could come up with two ideas. Well, you could, for example, globally reduce antiferromagnetic correlations overall in the entire system and make it a little bit easier for this hole to move through this antiferromagnet, so overall the energy cost is lower. Or you basically form this impurity solution, this polaron that we heard about, where within a certain range you try to modify the antiferromagnetic correlations or even turn them ferromagnetic. So within that bubble it's easier for you to move, the hole can delocalize a bit and minimize its kinetic energy a little bit, but only over this finite range. Yeah? And then basically this polaron would be anywhere in the system, so it would be a superposition of B at any of those locations in the lattice. And this is, I guess, Fabian, will you talk about this a bit more? How to estimate this? Okay, you can now estimate this competition between kinetic energy and magnetic energy. You can make some predictions on the radius of this object. A very simple calculation gives you this 1/4 prediction, a bit more refined prediction on this string picture that Fabian will introduce further, gives you this kind of 1/3 prediction. But it doesn't scale, so there's not such a dramatic difference in the scaling. It's anyway just a weak scaling with T over J, single particle hopping over magnetic energy cost in the system. Okay, now we can measure that, and I just flashed the results. So the idea is the following: you put holes in the system, not in a dynamic way. We want to compare the ground state, so we hold off the system. Okay, so we have this antiferromagnet with a few holes in there. It's cooled to as low temperatures as we can, and then we take a photo. When we take a photo, it might be that the doublon appears here. In the next shot, it might be that the doublon appears here. Okay, and now we want to know what are the correlations around this doublon. How are the antiferromagnetic correlations changed around this doubly occupied site? So what we do now is we recenter all the data around the doublon. That's what you see here. So we take all the data we get with the doublon appearing in real space randomly, look at the correlations around this doublon, and then we recenter the coordinate system around the doublon, and then we look at the different correlation functions. And here you see the C1 correlator actually. So this is the next neighbor spin correlator on the horizontal and vertical bonds. The white is kind of the background value, and already here you can see there's kind of a modification, the distortion of the antiferromagnetic correlations around this doublon. This gets even more dramatic if you look at the diagonal bonds. There you can actually see a complete sign flip of the antiferromagnetic correlations going from basically here positive ferromagnetic correlations along diagonal to negative values. And Fabian will explain you more how this actually works, how this comes about. No? Okay, good. And what there is the reasons for that, but this shows the strongest signal, actually this diagonals, they even reverse completely their sign. Now, one question you could ask, and you could do this even for C2, so it gets now a little bit complicated to plot, but I think the nice thing that you should take home, basically, that we can basically independently, completely model independently measure the magnetic correlations around our charge impurities. Okay, so that's the nice thing. And that's what we want to know, right? We want to know how this hole interacts with the magnetic background, how it modifies the magnetic correlations around it, and if we put more and more holes, how do these polarons maybe interact with each other? Yeah? So this is precisely what we want to know, and this is the tools we need to measure that, and these kind of independent of any model in the system. Because in the end, what you have is just correlation functions that quantum mechanics predicts you, right? And the final thing you can check in the system is the mobility of the excess charge carrier actually important for this modification, for this polaron formation. So what you can actually do is you can just pin an excess charge carrier. In our case, we just take a laser beam, we focus it on a certain lattice site. So now this doublon is pinned, it's fixed, it cannot move anymore. And now you could ask, does a static impurity give you the same modification of correlations, or do you actually need this mobility? And what you find actually that the mobility is crucial. Here's the case of the mobile doublon, or the delocalized doublon, and here's the pin doublon. And you can see in the case of the pin doublon, you do not see this polaron effect. So it's not just the impurity that you have got there, it's really the mobility of that impurity exploring its surrounding that basically modifies the antiferromagnetic correlations. Okay. All right, that's all I wanted to tell you on the spin part. Yes?
How do you prepare this doublon pin? Is it just you hope that there will be a doublon?
No, we actually, yeah, it's like when you turn on the laser at a certain depth, you change the local chemical potential. You basically almost deterministically form a doublon at that site. Okay, so that's a bit different than in the case before. Indeed, the doublon in the non-pin case is delocalized everywhere, and now we localize one to the tweezer. Okay, and you do that by just granting the tweezer depth, which changes the local chemical potential. So you just suck in basically a particle from the surrounding to form a doublon on that site. And that really happens almost deterministically. So in every shot we see there's a doublon at the site where we form the laser. Okay.
But then you let it evolve without it.
No, we don't know. If you would let it evolve, then what you would see is also interesting. Then you would actually see the polaron form. So you could do that experiment, and you could get an idea what is the time scale for now the surrounding, antiferromagnetic surrounding range. So what you're proposing is the following. You start in a situation where you focus your lasers, you have your 2D plane. Okay, you focus your laser beam here on this, where you have now the doublon. And now we said when the doublon is heavy, it does not change the antiferromagnetic surrounding. So now you don't have any antiferromagnetic distortions around that doublon, just a nice, perfect antiferromagnet everywhere else. And now you basically take away the tweezer, and now this thing can start to move. Of course, it can start to delocalize, and it will have some overlap with the polaron wave function. So you will form dynamically now surround this thing with the polaron cloud, with the distorted antiferromagnetic. But because this wasn't an eigenstate you started with, you will also have some excess excitations, which probably are some spin excitations that just propagate out in the system and thermalize. But you would dynamically, basically, in the vicinity of that doublon see that basically the polaron forms. Does that make sense? And you could measure like the time scale, how fast does this object move. You could also think about different experiments that measure the effective mass, for example, of such a polaron. You could build on that. You could maybe start out with putting a doublon here at the side of your trap in this antiferromagnet. And then, as we said, it would form the polaron cloud to remove that. But now this whole object would want to start to oscillate in the trap, right? So this whole polaron will now start oscillating left and right. And from the oscillation frequency, you could precisely determine, for example, the effective mass that Fabian introduced to you before. Okay, of this now compound object. And you can already see this has to be a heavy object, much heavier than a single particle, because it has to drag around with it this cloud of magnetic distortions. And for that to happen, for that to basically move these magnetic distortions, that's all going to happen on basically timescales given by the exchange coupling in the system. So these are like future experiments you could all think about in doing in these systems. That's I think really very nice and very powerful way of analyzing this. Okay, any more questions on this part of the talk? If not, then I would just, for the last 20 minutes, just at least want to mention a bit on a topic we heard from Ima is many-body localization. And I want to, so we're completely switching topics now. Since I want to show you that what the theorists are telling you is not just theory, it's really connected intimately to what we do in the experiments, very closely so. I want to just at least tell you a little bit about these ideas on many-body localization and how we measure them, and the big, maybe open questions that where the field stands. And for us to start with this, I want to actually go to work that we did together with Judith Altmann, and I should mention, Ima, did you mention our review? If you want to learn more about this, you can read, share a nice review. Well, I shouldn't say nice, you judge for yourself if it's nice or not, but that we put out recently on the subject. Again, there are many other good videos previous to that. And so again, I just want to remind you again, this scenario of many-body localization was a strong contrast to thermalizing systems. In thermalizing systems, we think of a subset in our system of having basically a thermal density matrix at the level of a total many-body ion state in the system, but we're now looking for scenarios where this fails in a robust way. And many-body localization, so in the context of interacting disordered systems, provide a way where we can break this in a very robust way. So some important points before we jump into the experiment. We don't know so much about MBL in higher than 1 dimensions. Most numerics is confined to 1D. High dimension is really hard because numerics is almost impossible in high dimensions for the level of systems we talk about. So this is a big open question. That's of course nice because we can use our quantum systems to provide some answers. And the other kind of caveat I want to make when we talk about when we do experiments in these systems and we look at dynamical evolution of quantum systems, this is important in this context, our observation times are limited to some extent. Okay, in our case, we can go maybe to up to 1,000 tau. What happens with above 1,000 tunneling times? Above 1,000 tunneling times, you start to feel that you're not truly isolated. Okay, there are couplings to the external world. For example, our laser beams are shaking a little bit, so they're heating the system a little bit. There was this black body effect. This is not important at this level. But there are other couplings to the external world that limit you. You would like to, of course, push this as large as you can, but I think any experiment will always be limited by some finite residual coupling to the external world. So that's something you have to deal with, because the ideal MBL scenario that everything is stationary up to infinite times, you will never have in an experiment. So that's a challenge. What can experiment then say about these questions? Can you have a sufficient separation of time scale to say something? And I'll show you some data on that. Okay, so the first experiment we did on that context was very closely related to how people looked at Anderson localization in cold atomic systems or photonic systems, so the non-interacting case, where you start basically with the local wave packet and you let it evolve, and if it's localized, it doesn't spread, so you basically see now the Anderson localized wave function, the probability distribution of that in this beautiful experiment, for example, of Alana Spee. And we do it in the same spirit. We try to create a non-equilibrium situation, and we try to see that we monitor the dynamical evolution of this non-equilibrium state. Now, the disordered system we choose as an initial experiment was disordered Fermi-Hubbard model. So Fermi-Hubbard you know by now very well. In 1D and 2D we looked at that. And this order we have is this actually not true disorder, and by now we don't speak of it anymore as disorder because David Hughes forbid us to speak about disorder in this context. So we actually have this quasi-periodic potential. So that's not true disorder because what it does, it lifts up and down in a very deterministic way the different lattice sites by this potential. And so now in a more modern language, David convinced us it's better to speak of a detuning potential, okay? Because it shifts the lattice sites up and down. If you have random disorder, it will do that in a truly random fashion. Here for this quasi-periodic case that we have, it does it in a deterministic way, but if alpha is incommensurate with the lattice parameter, then basically, in many cases, it's actually very, very similar physics that you're looking at. Okay, so now without interactions, this is the interaction part again that you also know from the Fermi-Hubbard model, you have this celebrated Aubry-Andre model, and for the Aubry-Andre model, which exhibits Anderson localization, we know everything. We know that for delta over J, tunnel coupling smaller than 2, all eigenstates are extended, and for delta over J larger than 2, all eigenstates are localized. So we just know that exactly. Now what we don't know so well is what happens now if we add this kind of interaction part in the system. So the idea to probe now whether a system is localized or not is the following. We start to prepare a non-equilibrium state, a very high energy density state, because as Dima told you, the physics of MBL is really the physics of high energy densities, not the physics of ground states. And so we start with a very high energy state, which is a state in our case where we have all even sides populated and the odd sides are not populated. Certainly that's not the ground state of the Fermi-Hubbard model, that's far away from that. Then you let it evolve over time, and you try to see as a function of time, you basically still read out a reminiscent or a remnant charge density wave as a function of time as a stationary pattern. If that's true, well, then actually you've proven that you're not in a thermal state, because in a thermal state there's no reason for the system to basically populate even sides, prefer even sides over odd states if you do a disorder average. So if you take a disorder average occupation of even and odd sides for a thermal state, there should be no difference how many even or odd sides you actually populate in the system. They should be equally populated. Alright, so here kind of first experiments on this, so we did that in this 1D setting of the fermions, and you see actually for the non-interacting case, for the no disorder case, at this interaction value of 5, approximately, you see you have rapidly equal filling of even and odd sides as you would expect. Okay. If you go to kind of now finite disorder cases, you see the situation is quite different. You see initial relaxation a little bit, but then you see that there's some remnants of this even odd staggered pattern still there, and it seems to be actually evolving into a stationary state, which tells you if this is non-zero, remember, that's not a thermal state. It brings us to an important point that basically to see whether the state is thermal or non-thermal, it's much easier to show that it's non-thermal, because you just have to find one observable that's non-thermal. That shows you that the entire state cannot be thermal. Whereas to show that it's thermal, that question came up in the discussion before, is actually a much harder question experimentally to say that the experiment is truly thermal. It might appear to be thermal in a few observables, but it could be that in other observables it's not. And unless you measure full state tomography, you really don't know that. Okay, I just want to show how dramatic interactions influence the system. We might say, okay, is it actually the same thing like Anderson localization? Here's some data for 2D quasi-periodic case of this Fermi-Hubbard model, where we have no interactions, non-interacting case, and we are in a situation which is way above the Aubrey-Andre localization transition. We may have non-interacting particles localized for delta equal to J. You know, all states are localized. And that's what we see actually for delta phi J. If I tune to non-interacting point with this Feshbach resonance, we see that this imbalance that characterizes basically our localized state is nicely going to a non-zero value. But we see actually adding interactions to the problem, how this leads to a dramatic decay of the imbalance. So now you've basically lost the localization properties of the system. So interactions dramatically modify, change whether the system is localized or not in the system. All right. Let me not go through the 1D data too much because I want to stick to the open questions, big questions, which are mostly connected to higher dimensions. And the question how we can probe for MBL in higher dimensions. And so, again, I said numerics is difficult here, so we do an experiment. And how we do the experiment in this case was the following. We made this order, we projected this order onto our bosonic atoms, in this case, in the lattice. So we take this BMP that I introduced to you, we print a random kind of random disorder intensity pattern, and we project that onto the atom. So that's nice because you see now that this order is not externally generated. You really control it by the light to shine on the atoms. So you have complete control over the disorder pattern that the atoms are exposed to. Okay. And we can actually measure that. So just to show you that it actually works well. Here's what we expect to project onto the atoms, these gray levels of intensity, which lift up lattice sides up and down. If we send it through our objective, then this will be slightly blurred because the objective has a point spread function, so it's a little bit smoothed out. And now we can actually measure the energy shifts. Now we can go into every side with a quantum gas microscope and measure how much is that lattice side lifted up or down in energy. Okay, this is what we expect. This is what we measure. Okay, and actually you see there's actually quite good agreement between both. So you see, for example, this ring here corresponds to this part here, this blob is this blob here, this line is this line here. So we basically can completely, with a quantum gas microscope, experimentally characterize the disorder at the level of knowing what the level shifts on single lattice sides are. Okay, and now you have the distribution of energy shifts, and then I can plot that. So this is now the distribution function. How often is the lattice side lifted by a certain value delta I? This gives you this almost Gaussian probability distribution, and the width of that characterizes the disorder distribution that we have in the system. Okay. All right. So now let's do the similar experiment Yeah, this is actually interesting just to show you that true random disorder and quasi-periodic are really two completely different things. Just if you look at the probability of occurrences of energy shifts, you see this is what you get for true random disorder. Here, for example, the Gaussian probability distribution for one case. But quasi-periodic, what we had before, has this very different probability distribution of energy shifts. So there are fundamental differences, but I don't want to go into the details. People are trying to understand better what exactly these differences are in the transport that occurs in these systems. Okay, so as I said, how do we probe now for thermalizing or non-thermalizing behavior? Well, we just make a non-equilibrium state, and in our case, we start with this one insulator of bosons, and then we just create different non-equilibrium states. Either a domain wall or this layered cake in film, we just remove every second side, or we create a different charge density wave period. All of these are obviously non-ground states, and now you let them evolve. Okay, and now you try to see if there's a steady state reached. That's good, because then you can at least hope that you're seeing the physics, the true, genuine MBL physics occurring in the system. Caveat, asterisk, is always experimentally limited up to the time scale we can observe. If something would happen on 1 million tumbling times, we cannot say anything about that. And then we analyze if there's a random pattern there, because if the random pattern is there, we know it's non-thermal. So we do that for the domain wall here in 2D. And here's a single snapshot how this looks like. You start with this domain wall. It evolves over 250 tumbling times. And for no disorder, well, happens what you would expect. These particles just spread out in your trap. And if you average over many of those shots, you see actually that they form a nice spiritually symmetric density distribution in your trap, as you basically would expect, comparable to the thermal state. Whereas if you are in this disordered case here, delta over J13, you see that even for long time evolutions, you see a remnant domain wall in the system. So obviously this is not a thermal state. The thermal state in this disorder potential would be also spiritually symmetric. Okay? And now we can say, okay, but is this really evolving into a steady state? Or is it just relaxing slowly? Well, as good as we can say, indeed, it evolves into the steady state. Here's this imbalance which characterizes how much of this remnant domain wall is still there as a function of evolution time, how this looks in the experiment. So low disorder values relaxes to 0, large disorder values seems to be relaxing to this constant value that you see here. So if you now plot this imbalance, again, which is our proxy for thermalizing and non-thermalizing behavior, you see that up to some disorder strength here, everything relaxes to 0, which is compatible with the thermal phase, aquatic phase. But above some critical disorder strength, you see now you get this finite imbalance, this non-thermalizing behavior, indication of this localized phase of the system. In this steady state, we can actually take the closer look at the density profiles we get of this domain wall, and we see that they have this exponentially decaying profile, so we can extract a decay length from them, and this decay length actually diverges precisely at the point where you have the disorder strength taking the imbalance to non-zero values. So this is really an indication of some phase transition happening in the system, some divergent length scale occurring here, which does not correspond to any kind of normal kind of phase transition we basically know in the static process. Just to connect this to Anderson localization, just to show you that this really is dramatically different than Anderson localization. In 2D, Anderson localization, similar to 1D, occurs for arbitrary weak disorder potential. So for a non-interacting system, you put arbitrary weak disorder, epsilon disorder, and the system immediately localizes. That means for our domain wall experiment, we should see the imbalance of this domain wall should be non-zero for arbitrary weak disorder strengths. Okay, and that's basically what you can see here calculated from numerics. So this is what numerics expects for the non-interacting curve. You ask why are there no data points here? Well, that's just basically when the system size becomes smaller than the localization length. Okay, so the system just has to be made larger. But I think what's important here is that arbitrary weak disorder immediately leads to non-zero imbalance, whereas the interacting case behaves completely different. You see, the interacting case, the data I showed you before, shows this very dramatically different behavior that you see thermalization up to some disorder strength, and then only this non-thermalizing behavior above a certain disorder strength. And we can dilute the system to make it effectively more non-interacting, and then you can indeed see that this transition point shifts towards the Anderson localization point, which at least makes sense, which we should really expect for the system. Okay, I don't want to, just show you, maybe this data is also kind of very nice, just to show you that really this steady state that we see, we try to extend this to as long time scale as we see. We tried this, for example, with this layered cake structure where you have this strike pattern and you look how that evolves as a function of time, and we can monitor this up to 1,000 tunneling times in the system. So we see up to this 1,000 tunneling times, we see this plateau persisting very well in the system. So we have confidence, or we, at least from this experimental data, we would say that MBL exists in this 2D system. Okay. Now, of course, again, to be devil's advocate, if there is a very, very slow decay that on a million tunneling time scales or 10 to the 8 tunneling time scales would relax the system, we cannot say anything about that. Because at this point, beyond a few thousand tau, we are getting coupled to the environment too strongly, and coupling to the environment, remember, will always relax the voltage rule. Okay? But that's something that any experiment will face. This challenge. So we always try to see, can we get evolution into some kind of steady state, and then for even longer timescales maybe relaxes, but if we can see that, we believe that the general MBL that is happening on these shorter timescales gives us some indication whether MBL exists or not in the system up to these experimentally measurable accessible timescales. Okay, just to finish off, I just want to show you that one nice thing one can try to do is to structure the bath and to talk a little bit about some of the avalanche effects that were mentioned before. So one of the questions in 2D is, if you put thermal inclusions into such a disordered system, do they destabilize the entire system, or does MBL persist? Okay, so how stable is MBL to thermal inclusions? In these thermal regions, which would be non-disordered regions, the gas will thermalize, as we know, we understand. And the question is, how do these thermal bubbles, how do they interact with the remaining atoms in the disordered potential? So that's one of the big questions in the field right now. What is the stability induced by such thermal bubbles, or instability? Do they lead to avalanches, thermalizing properties? We know absolutely very little about timescales of these instabilities. Even in 1D, this is extremely hard to see. In 2D, there's basically no numerics that can tell us anything about it. So we really try to do these experiments and answer that. And I think that maybe strong point is to say why the quantum simulations are really nice, because you can structure the disorder in a completely controlled way. You can shine whatever kind of disorder pattern you want with whatever kind of thermal inclusions onto your atoms, because you control the disorder. It's not in the material, you shine it with your light field onto the system. Okay, so that's, I think, a very nice property to look at, and that you can analyze the system in this very controlled way. I don't have time to go to the transport cases, so I just want to basically flash a few big questions, I think, that remain in this field of MBL. I said we still don't know much about MBL in higher dimensions. Experiments so far seem to indicate that MBL exists in higher dimensions, in 2D at least, what we saw, up to the accessible timescales, always that caveat. If there is an instability, we would of course like to know at what timescales that occurs, at the age of the universe, then it's irrelevant to any experiment, or does it occur on shorter timescales. What are the transport properties in the thermal phase before you actually localize? There should be profound differences between the quasi-periodic scenario and the true random disorder scenario. I think that's also unsolved theoretically. They're completely opposite predictions for what's happening to the transport in that regime. How can we measure this localization then? How can we actually precisely define it? That's something you might want to press Kima on, or some of the experts. How actually, in Anderson localization, it's clear. You have an exponentially decaying wave function, you have a localization there. How do we define such a corresponding object in the MBL case, and in a kind of consistent way? The field does not have a consistent definition of what localization actually means for the MBL case. Also, we'd like to know again how, when we couple such MBL systems to baths, finite size baths, and for large baths we know that's fatal, that will always destroy MBL. So if we have a huge bath, we couple it to a localized system, that will destroy localization MBL. But for finite baths, we don't really know comes back to the question of the bubbles. That I, from the point of view, what do we need? Well, we'd like to go to even longer time scales. So can we push maybe 10,000 tunneling, 100,000 tunneling times? Can we go to larger systems to look at some scaling effects, finite size scalings? Can we work with the structure disorder that I shaped you, or can we, in general, improve our isolation from the environment to just make the system cleaner and exceed our time scales and system sizes that we're looking at with these systems? All right, I think that's everything I wanted to tell you, giving you an overview of very different experimental fields, and I hope in conjunction with the theory clause, it shows you that this is not just abstract theory, which some of you are working on, but this is really very relevant, highly relevant. I don't know, this was not meant in a derogatory way. I'm just saying, I think,
experimental side.
I remember when I entered this MBL field, there was no experiment, zero, and hundreds of theory papers. I would say that's not a good situation for a theory. There's absolutely no experiments. So now we are, of course, in completely different situations, and I think it's wonderful to see, I hope that Bloch conveyed that between theory and experiment, there's really extremely close collaboration and making big benefits of the new experimental techniques that we're doing. All right, with that, I'll leave you with this nice picture of Munich. Just somewhere around here, around the corner. Thank you very much.
What does Hamming distance measure? Is it like something like cross entropy?
In this case, it was the flip. In this case, you get the number of configurations, how many steps you need to make to flip the configuration between the initial state and the final state.
Okay.
And this was related, in our case, can be related to this imbalance, as was shown in this paper by Marcus Heil, the reference. This imbalance actually is connected to this Hamming distance. Basically, how many configuration changes you need, how many flips do you need to make to go from one configuration. Yes.
For this MBL topic, do you run really out of time, or what would mean if you go to higher energy scales, you would make more steps? Or
we are already at very high energy densities in the system, and as we said, that should not change time scales in this process. So we are already working at high energy densities here, and time scales should not change, very much on that energy where you are in the spectrum. Given that you are at some point, high energy density in the system, things should not depend dramatically on that. So I don't think that's also what we see. A lot of the dynamics does not depend very much whether you start with charge density wave 1 pattern or charge density wave 2 pattern in the system. That doesn't really depend very much on that. So I think it's really, in our case, to show this data again, this one here, the real challenge here for us, we really want to push this to longer times. Here you would say, okay, fine, this looks like a nice steady state that you evolved into after some realization. This, of course, you want to understand what is the time scale of this relaxation in the system, how does it depend on interactions in the system, but then you say evolve into this state which is like certainly a non-thermal state. And so you really now want to see what happens for longer times. And I think that's the caveat that many of these instabilities that people have put forth, we have no predictions for the time scales of those instabilities. So maybe they occur, but maybe they occur at the age of the universe for our systems. And then maybe from a theory point of view, you would say MBL is not a phase, because eventually it will relax. But from a practical experimental point of view, I would say, well, how would I tell the difference? Okay, so but we're touching on grounds where it's difficult. Yeah, but certainly, if I could show you a plot where this extends 10 times longer, you would believe me even more. So it's certainly good to have a more accessible range. To constrain a possible residual slope on this data. Actually, within our experimental error bars, this is within 0 plus minus can be positive or negative slope we measure with fluctuations.
What can you tell us about related experiments with the generalized Aubrey-André model?
Sorry, the what?
The generalized Aubrey-André model.
Yes, what do you want to relate to it? Localization?
Yeah.
Yeah, so what we looked at, so this is a bit for the specialist, in this generalized Aubrey-André model, you have a model where in the Aubrey-André model you have, so you basically remember in Aubrey-André you have delta over J, and there are 2, I said all states are localized, and below 2 all states are extended. Now, so this is Aubrey-André. There's also a model called generalized Aubrey-André, which can be, like, for example, introduced by longer range poppings or other possibilities, or actually also shallower lattice depths in our case, where you actually find a regime where you have coexistence of localized states with delocalized states, separated by a so-called single particle mobility edge. Okay, so there is an energy, so there's a range here, down here, where you have coexistence of extended and localized states, separated by critical energy, the single particle mobility edge. And now the interesting question is, for such a system where you have coexistence of localized and extended states, if you populate them both initially, do the extended states influence the localized states? Do they destabilize the localized states? Is there some interaction between them? Do they change the relaxation dynamics in a remarkable way? Do we get a many-body mobility edge because of this coexistence? So these are, again, big unknown questions. What we find, we looked at this a little bit, we didn't see any difference in relaxation transport properties and relaxation dynamics in this generalized Aubrey-André model compared to the Aubrey-André model. That's as much as I can say, at least for the things we looked at so far. But it's an important system, and it's kind of a prototypical model system, because you want to know, again, it comes back to the question I talked about before. You introduce delocalized states, extended states, like also in this bath question, where you have this ordered system, and you have extended states here, thermalizing states here. What happens when we have these thermalizing states in contact with a localized system? A little bit, this is the variation of that. You have extended and localized states, and you ask, do the localized ones localize the extended ones? Do the extended ones destabilize the localized ones? Do the interactions? So that's a that's one of the big open questions.
In the thermal phase, I may have discussed this, but in the thermal phase, can you see that the energy density is basically uniform? Like if you look at if you can extrapolate something about the energy density on top of space.
So for kinetic energy, we're basically in an infinite temperature. So we remember when we make these localized wave packets. Localized wave packets means you occupy homogeneously all the Bloch waves in the kinetic energy. With respect to kinetic energy, we're basically at infinite temperature. And of course, that we can translate into an energy density, because I know the bandwidth of my kinetic energy just distributed with my particles. And then I can have different initial states where I can have, for example, doublons or no doublons. And if I have doublons, then I have some interaction energy as well. And we can have different scenarios of tuning kind of the energy density of the state, like, for example, having doublons or avoiding doublons, starting out with them. So that will gives us some access in tuning the energy density of the system.
Right, but you would expect in a thermalizing state for that to spread out uniformly, right? And when it's not uniform in your initial state.
Well, initially, for translation invariant, there's the trap, of course, always. If you use some heterogeneity, if it would be for the trap, an harmonic trap, it would be for how we reduce the initial states would be uniformly distributed. But you could make a state where you create a high energy density initially at some point in the spread and ask how does energy transfer, or use energy transfer as a proxy for localization, particle transport. You could do that. You could just maybe modulate the laser at a certain point in space or a region, keep the atoms locally, introduce some energy density there. It's not thermalized yet, so if you reach an excess, you can look how that spreads out. That's certainly interesting.
Other questions? No? Thank you, Immanuel.